Yes. And yeah. I've got an email saying that this person cannot open PDFs. Can you open PDFs? I didn't get it quite straight. I mean, I don't know. So I just want to reconfirm if you can open those PDFs that are linked, anyways. Okay. But if you experience any problems, be specific. What kind of PDFs you cannot open? Then I adjusted a couple of deadlines. So let me see. So the deadline for home assignment 2 is now 15th of December, just before the second quiz. So before it was, by some reason, it was 22nd of November. The first quiz be on home assignment 1. Huh? Will the first
Yes,
yes, exactly. Yes. No knowledge representation should be expected on a quiz. And yeah, talking of which, the quiz, you see it already in Canvas here as an assignment. So if you click on it, so you see that it will be available starting from midnight on 22nd, and will be available to take 24 hours. So you can take it at any time. Yeah. Say again? No, it's. I mean, this is a quiz that tests like general level understanding. Well, I mean, part of the assignments I considered during the classes. So, like, for example, today we will do some calculations which you can find useful, so to say, in for this first quiz. But otherwise, so this chapter, and when you read about standard logics, so that's what will be tested. No rocket science, just
Is there a time limit?
yes, it is. I just I can return to it after during the break. I will double check because in this mode I don't see it.
But is it like the other course we have with you that is like 40 parts in the one?
No, it's just one part. It's a single part. I think it's 1 hour and a half or 2 hours per attempt.
Because some parts in the other course were sort of tight.
Yeah. By the way, it would be good to know. I mean, because I didn't see any. I know. Yes. But to me, it was hard to kind of for talking about the other course. So it was hard to estimate since this was the first time I migrated it from Inspira. But any feedback on that is welcome. Here, let me see if I can. No, I need to go to the settings of the quiz too. I will do it during the break. Okay. Yes. What else? What else? Another novelty is home assignment 3. So you can again. So you either find it in assignments or here in the modules. So home assignment 3, 2024. So and this is how it works. I want to kind of speak loud about it. So you will be given a base article, which is called Symbols and Grounding in Large Language Models. So that's what I announced during the first class. Compared to the last year edition, I changed the thematic focus for the assignment 3. And I personally found this article very interesting and informative. It's not heavy reading whatsoever. It is, on the other hand, rather broad and touches upon fundamental challenges of artificial intelligence and to which extent current large language models address these challenges. And specifically, so just to give you example of these challenges, so it's a challenge of symbol grounding, symbols, whether you can learn symbolic representations, question of compositionality, and to which extent neural networks, modern neural networks address this challenge. So this is the article, so it is linked from here. It's open access. So you can read it either as a PDF. Okay, so chunks. Let me see. How deeply we expect it to. Yeah, I will come back to it. Yes. So there is an online version, but you can also download PDF of it. And so there are no, it's a reviewed or survey type article. Also they claim that it's not a formal literature review. So I consider it kind of very educative education. Yes. In addition to this, so I want you, well, in this very course, I want you to do kind of research. So I don't assign you. This is the base paper, so you need to summarize it. So the basic concepts. So at the end, your output from this assignment is a presentation, PowerPoint presentation. So kind of summarizing the content of this paper and up to two more. So the cutoffs for points are like this. So you may choose to summarize only the base paper. Then it will give you some minimal number of points, 80, which in addition to the other two assignments, yes. No. It's a kind of um, uh, you just upload, so it's a written assignment. So, but instead of writing an essay, so you create a PowerPoint presentation. No, you don't present. We are too many. I would love to have it in a presentation mode, but we are just too many for this kind of exercise. Yeah, so you may choose to go and review only the base article, so you get the minimum number of points. So together with other two assignments, it will give you in total points enough for grade 3. So, or you can choose to go further and dive deeper into certain concepts that you personally find interesting. And here I don't want to impose any kind of random assignments or anything. So really kind of interest based. So, and there are different areas you could be interested in. You could go deeper into large language models, and there are some links in presenting experiments on how people understand, explore the symbolic nature of it. You could go, for example, I find it kind of personal, go back to the roots, to the definition of the challenge of symbols compositionality. So what do people mean? And there is a one fundamental paper that people are still referencing to. So it's a paper by Fodor and Peletian that just argue about impossibility of neural networks to learn symbolic representations, because so they define the properties of what would it be and argue why not. And then ever since, so yes. Um, a knowledge base. So if you have picked into the second assignment, so how to represent a knowledge. I mean, what we do here, all our knowledge, like written, this is symbolic, and we operate on symbols. Inside the brain, we have neural representations. Somehow, we are able to kind of convert these neural representations into symbolic knowledge, yes, and do inference based on symbols. But so my hope is through this assignment you will understand that it's not very trivial to um, uh, for the artificial neural networks to do the same thing. So, but again, so this is a base course. I just hope that it will wake some interest in you in certain directions. Or what I also found interesting while reading this paper, this question about grounding. So, what is symbol grounding challenge? I mean, I think I mentioned it in the beginning, but how do you understand it when you hear symbol grounding? I mean, symbol, yeah.
Was it something about grounding in like ground truth?
In the physical, yeah, this challenge is about connecting abstract symbols, symbolic representations, to physical objects, which we observe and explore via our sensory inputs. So, because otherwise, I mean, you can do a symbolic system totally without grounding, but I mean, then I mean, the system exists kind of in its own world without being connected to the reality. And normally, so people say that neural networks have uh, immediate grounding or native grounding because for example, if you train a network in a classification for a classification task, so at the output you have some categories, so class 1, class n, and on the input you have, for example, images like raw pixels. So and during the training process you do this kind of grounding of these concepts to the pixel intensities. But what is interesting with the large language models, ChatGPT and such, they are trained on texts. And at the same time, so we are presented with good evidences that they do or they expose really kind of uh, good understanding of concepts. So it's like so they can explain all the way to down to parts and such. So the question is, what is grounding in this case? I mean, because we never so this system is never exposed to um, physical representation of the objects. But apparently, it's kind of philosophical question because I mean, our language is very rich, and there is certain concepts they exist only within the language, and so you will find this chapter in this paper. So and then so maybe you can dive deeper and go into this more philosophical area about what grounding is. Um, yeah, but nevertheless, so and so if you aim for the highest grade, so you review second extra article. That's it. But again, so the review, I mean, I want to see conceptual understanding. So if you happen to select like highly technical article, I'm not asking you to follow all the formulas and then go deep, but really I mean, sometimes you can get meaning without really understanding the low-level details. Yes. I think I said pretty much everything. But if you have any questions, so please also use Discord for this. All right. So today we will finish the topic of logical agents and standard logics. And to finish it, I want to talk about higher level logics. And so that probably would also address question in the chat, to which extent you need to get an understanding. So I will present an example. So and that is this level of understanding you should expect for the quiz. So again, I would regard this example or this level of understanding as conceptual, still conceptual. So we don't go into complex logical reasoning and such. So kind of, but you will see and you can ask a question. So high level logics. But before going into high level logic, so we talked about in the previous three classes, we talked about propositional logic. So this is the simplest logic system for formal logic that was invented, so to say. What is its characteristics? So what can you express in terms of concepts? So how does it describe concepts or the world, the world?
Sentences and facts.
Yeah.
Oh, yes, sentences and facts. It's knowledge base.
Yes. So it operates on variables which are facts known about the system. So and those facts, importantly, those facts are logical. So they're always binary, true or false. So we kind of look at our world from the point of view of everything being true or false, black and white, so to say. Higher level, higher order logics, compared to propositional logic, use quantified variables over non-logical objects. So we have our physical world. So in this world, we may have table, and we can have what's fork, spoon. Objects. And importantly, these objects are of non-logical type. So they are very complex objects. And then we may have variables, obviously, in this world. So we somehow may group certain objects and say, okay, so this is a variable. So we have okay. Um, but then we want to do some reasoning, some logical reasoning on this. So it means that we need to transition somehow to our logical world. And logical world is where all the objects they as we dealt with them in the propositional logic, they either true or false. So they are truth values. So, and we want to map somehow this physical world into this logical world. And we do it by functions. And these functions, so these functions, they can reflect different stuff. So they can reflect properties, colors, texture, structure, material, and such of an object. Or it can reflect a relation. So something on top of one object on top of another object inside another object. So this kind of relationship. So relations. So and this functions. So in standard logics, they are called predicates. So, for example, example of such a predicate on object table. So, in essence, I mean, from the syntactic point of view, predicate is a symbol. So, is a symbol that is used in formulas, and functionally it maps the real world objects into the truth values. And here again, so if we take it on O table, so this would be, for example, a variable. This can be well a constant, so an instance, or another variable. So it's kind of very flexible. And so it maps in this into true or false. But if you, in addition to this construct, so the functions that map objects to the logical world, we need quantifiers. So we can build sentence for one object of a kind or for all objects of kind, and those are called quantifiers. So there are two quantifiers. Good news. So universal and existential. So universal. Oh, very unfortunate symbol I chose. And existential. So which in plain language is translated as for every, and there exist. And one, again, basic relation between these two quantifiers could be, for example, this one. So not or well, actually, let me just rewrite it some long. Or well, it's I think I'm complicating the stuff unnecessary. I will make it right now. So quantifiers is always over variables, and then you have some formula where this variable is involved in, and so this equivalence tells that you have this O and not formula. So this is one of the basic equivalences that you have to remember and use, as we will see later. But but back to higher order logic. So higher order logics. So in general, all of them use quantified variables over non-logical objects. So this is the definition. Now, again, very quickly about the difference between these different logic. So all of them belong to what is called standard class of standard logic. So, and here as a summary, so we talked about propositional logic. So today, now I will talk some more about first order. And yeah, in general, there are many other higher order. So here we do not use predicates. We assume that facts are already in the logical domain. So the whole world is described via logical variables. And as such, atomic functions, atomic logical functions, so they sometimes called as zero place predicates. So, I mean, it's already kind of converted. All variables are in the first order logic, so we have these functions that map the real world into truth values, but they are very simple. They capture simple relationships, or they are simple predicates, and they are equivalent to sets. So so set, and they reflect belongingness to a set. So interpretation of predicates as sets. In addition, in first order logic, so we have quantification over variables. So that's why I was kind of stuck here. So we use quantification over variables. And well, again, so just to extend this definition, in higher order logics, quantification can be extended. It can be over predicates, functions of predicates, very complicated structures. But why bother? Why do we need it? I mean, if you look at this transition, so what do we gain by increasing the order of logic, or inventing a more complicated logic mechanism? So what do we gain by this? Expressiveness, richness. So we can describe very complex situations from the real world. So using formalism of logics. And they all built on top of each other. I mean, so again, so, first order logic. I mean, we can have an entire module on that. But on conceptual level, so I want to present a simple example, and at the end, so we can see how these manipulations help in interpretation and verbal interpretation of a formula. So now consider the following equation. So not for all items on item table implies there exists item let me continue. There exists item on J and I always kind of confuse this up and down, so I write it mainly for myself. And not touch I J. So here is a sentence in the first order logic. So have a look at it. And maybe I give you a couple of minutes for that. And tell me how we go about interpreting it.
And therefore, go.
Yeah.
We have something.
Okay. Yeah, go on. So I will speak louder here.
So there's like the negation, and then there's like the upside down. So there does not exist an object on the table, which implicit that there
Implies.
exists one or something. There exists something on the floor, right? And there does not exist something, and then I cannot read the
Touch.
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 Touch. And it does not touch IJ. something.
All right. So touch. Doesn't make sense. What about Zoom? Let me just maybe say again, but I mean, you tell me and I say because they don't hear. Yeah, say again.
Yes. So there does not exist I on the table.
It doesn't exist I on the table,
Any I.
any I on the table,
Implicit that
which implies
that there exists some J on the floor and it does not touch IJ.
there is some J on the floor and doesn't touch IJ. Something like that. Yes. But okay. But let's see. So this is a little bit complicated sentence. So we probably need to and I think for interpretation, it probably requires some modification. So yeah, it's rather tricky to make sense, like good sense or a simple sense out of it, because I mean, what you say, it sounds kind of, you know, sometimes logical contradiction is like, what is I? And yeah, let's sort it out somehow. For starters, first order logics, they are quantified on variables, right? So quantification on a variable, and then you have a formula. So what is a formula here? Where does it end? Where does it begin and where does it end? That was the first kind of pitfall that you were falling in. So you started to interpret for every I on table implies. In fact, this sentence, so this is syntactically correct sentence. So the formula here is this one. See the difference, because it is quantifier for everything that includes I. So something is about relation of I and another object. Yes.
Yeah. Just to clarify the syntax, maybe you should put a colon between the quantifier and the rest of the sentence. We did that though in discrete mathematics.
Hold on. I don't think it's a standard syntax, but I mean, okay. Yeah, okay, fine. I mean, I can do that. Yeah, absolutely.
Use that.
Fine. Then I use it as well, in addition to discrete math. But I mean, call to your knowledge from the discrete math. So how do we deal with this equation or formula?
The says that since like the quantifier A, right, there exists I mean all I, right?
So
For every I.
so this example is about application of this basic equivalence. So let's and first of all, so if we look at this formula over here, so again, so let us somehow simplify it. So so we have implication. So and it can be written as I. So let's just denote the x, and this part is y. So x of I implies y ij. So we apply the conversion of this negation of universal quantifier and convert this sentence into the following. There exists I such that, and then you should negate the sentence, this x of I, y. So there exists I for which this holds. Now we apply this elimination of implication. So basically not x. I skipped the indices. So not x or y, which is equivalent to what? X and not y. So this x for us is on I table. So this is our predicate. So let's figure out what not y means. So not y, it will be not J. And not bunch. Um, mhm. Here again, we have negation of existential quantifier, which can be rewritten as for all j not and this thing. So now we see that this negation of this part, so we have and conjunction as part of the formula, and that means negating one of the terms would negate the whole thing. So if we negate second term, so this will hold true. So basically, this part not y. If I just rewrite it, then it will be on j there exists j such that on j floor and touch I j. Hmm. So now putting everything together. So starting from here. Oh, I think so. You don't tell me. So I used the wrong quantifier. So the final formula, if we look this the one that we started from, so this is 1. There exists I such that on I table and for all j such that on j floor and so this is a initial statement, initial sentence in the first order logic rewritten as existential. So from we transitioned from a universal quantifier over I to an existential quantifier, that there is such I on the table. And now you continue. So how will you say?
And for all objects J that is on the floor and touch I touches J.
Yeah. And this is a little bit different from your original interpretation.
Yeah.
Again, this is maybe a little bit complicated example. So you won't construct it from scratch, but so which exemplifies the transition between the quantifiers. So in this case, it leads to better interpretability. How, so it is not specified, so I didn't specify how the equation in the, I mean, the sentence in the first form came along. So, but so this is type of math you do with first order within the first order logic. So as you see, it's a combination of propositional logic. So so on this step, for example, and as well as introducing the quantifiers. That is interpretation of a set. So one of many, all, and such. Yes. Any questions on this example? Okay, then let's take a break and we start with something different. I continue recording and I start sharing. Can you quickly confirm? No, you don't see anything now.
We can see.
All right, good. Yeah, so let's do something different. So again, so far we talked about standard logic. So situations about world are described in sentences. They what is it? Consist of variables, operations on them. So variables could be transformed from real world objects using these predicates. But so what is common to if you talk about the nature of these variables, what is common property of them in standard logic? The nature of variables. They are exact. So when you make a predicate, or in the propositional logic, when you introduce a variable that describes a certain fact, so it is exact. It is either true or false. So what about situation when we want to describe world with some uncertainties in our judgments? So you can describe, for example, functionality like of this dishwasher in very vague terms, like dishes are dirty, use hot water. Many dishes use more water or more detergent. So how to quantify this more? I mean, these terms that are not exactly specified. So this would be the topic which is handled by something which is called fuzzy logic. And here I just want to give you a taste of it. So very basics, just to complete the picture with the standard logics. And to do that, so let's do this mental experiment, and let us try to quantify such a not crisp concept. So, for example, how would you quantify old? So a person is old. How many years is old? So let me just do this. We have only 6 people. So we have incredible statistical data of 6 values. So what is old for you?
Maybe above 80.
Okay, 80 plus.
It's a bit like a philosophical question.
Yes, it is. 65. I mean, if you ask my 7 years old daughter, I'm bloody old, you know. So what about you?
50 plus.
50 plus. Okay, 50 plus.
I'm not sure. I mean, to some extent, it's relative. I mean,
Of course, and it's very subjective, not only relative, it's very subjective.
I'm very old for a 10-year-old. Like for being 10 years old, I'm very old.
Yeah, but I mean, normal.
I don't know if I can actually.
Yeah, it's a good point. But you see, I mean, sometimes you're face a question which you need to provide an answer. So um, irrespectively to the context. So that's, for example, how the social surveys are done. So you're asked the question, and you're that statistical sample that provides answers. And of course, I mean, the nature of question can be very broad, but at the same time, when you are asked, or it means that probably you are selected as a reference group by or a group of experts, and you answer from exactly your perspective. So not in relation to just general formulation. So now I'm asking you this question more, I mean, in position of your age and your experience. So this kind of restricts to the values to certain kind. So what was
I think I'll take around 65-ish,
okay,
pension age.
65. You guys,
60.
and what about you? Huh? 70, yes. Oh, you make my life not very. Okay, so let's put it say 50, 100, 50. Or maybe we start from 50 to 100. Yeah, 75. Yeah, something like that. Value. Old. Oh, sorry, I inverted the axis. Score. So here we will display the frequency, of course. So 50, 100, 75, 60 somewhere, 80 somewhere here. And we had very few answers for 80 plus, maybe 0 even. Some same for 70. So lots for 65, and then no, this is 1. So the frequencies. This is more or less the distribution of answers. Yeah, so that's what we did. We constructed a so-called membership function. So where we translated some otherwise crisp values into a score. So let us see. Let us continue. So I will come now close to the actual definition. So, I mean, this situation is very typical in real world. So there are many, many cases where statements they do not have a univocal truth value, either true or not, or false. Take, for example, measurements from a sensor, like a temperature sensor or pressure sensor, depending on well, first of all, it's a function of the environment, so there are some deviations. But even if the environment is pretty much stable, so still the measurements can be different depending on the manufacturing process, so to say. Then again, so we are talking about cases where we base our reasoning on the opinion of experts, and these experts can have different opinion about your question. So that's why we need this machinery to incorporate all these uncertainties or fuzziness, in other words, into our logical reasoning algorithm. So we want to transition from exact definition of variables into fuzzy definition of variables. And here we have a couple of definitions. We have a linguistic variable. So it's a concept that you want to get an estimate of the value from the experts, for example. And they're used to define this variables used to define membership in the fuzzy logic. So membership function. So that's what we try to construct here. So it's a function describing a subjective judgment about a linguistic variable. So we here we try to come up with a membership function for concept for a linguistic variable old. But it can be, as I use this example in the slides, so it can be, for example, variable ripeness, so the readiness of a fruit. And as you see, so we map some crisp values, so exact values, some instances, into a score. So here, like 60 is the highest score, and then according to this function, let's say 65. Well, 65 should be the highest score. 60 would be somewhat less, but I don't know, 0.8 and such. And this is our subjective. This is our fuzzy range. Yeah, over here. So membership functions can be obviously can have different shapes depending on the question and or the phenomenon in question that you try to quantify using this way. And it's actually unique nature with respect to uncertainties of definition. So here we have, for example, 3 linguistic variables, unripe, ripe, and overripe. So all being quantified on their own with their own membership function. And then membership functions, even that one that we have constructed, so they could be fitted into some mathematical form so that you can compute actually. So not necessarily that you need to use this table form. So you can choose one of appropriate functions that best describe certain shape. So they can be a triangle function with clear defined mean, and then a decay equivalent decay, symmetric decay at both ends. So it can be skewed or sigmoid-like functions, or functions that could be approximated by standard distributions and such. So there are many. What to choose, it really depends on how your answers or how the distribution of the fuzzy range values depends on the offered score for your linguistic variable. We will not go into details of fuzzy logic, but if you want to know more, so there are a couple of very interesting tutorials like this one, so to get more details on it. And MATLAB, for example, as well as Python, obviously, has libraries and tutorials on how to do it. So how to build expert systems based on fuzzy logic. So if you're interested, so you can start from there. I just want to show you the basic manipulations with this membership function. So which is actually not very complicated to begin with, and resembles operations that you do with standard logics. So first we define a fuzzy set. So we have we describe a given phenomenon through different linguistic variables. So for example, the level of readiness of a fruit or a corpse, you can define using 3 variables roughly. So unripe, ripe, and overripe. So find your own examples for, I mean, age, young, middle age, old. And so you basically define this. You have set of linguistic values along with their membership functions. In this way, so you can represent even numerical values again. So in when you decide the kind of the granularity of your bins, so how you want to define. For example, if you take this voltage, so and you want to kind of characterize your range of voltage levels starting from, say, low negative to medium negative to around small negative values or small positive. etc. So you approach problem of defining fuzzy set first, identifying the bins and how you characterize a given phenomena, and then so you either make an assumption, so an educated guess how you want to have it. So like with numerical values, it's maybe, I mean, you don't need to ask experts, right? So that's up to you how to design. Some other fuzzy sets involve communication with experts, for example, to build this kind of function. But having this in this way, you can describe your set of values. And then you can do operations on these fuzzy sets. For example, you can do a complement of a fuzzy set, union, and an intersection. And that you do by evaluating membership functions. And you can define it in different ways. So here is one way which resembles closely the logical operations. So now when we defined, or now when we are equipped with this way on how to characterize fuzzy sets, so how to characterize fuzzy concepts via linguistic variables and membership functions. So now we can approach reasoning, so inference. And inference involves several components. So first of all, you need to have some rules. So exactly as with standard logics. So you should have a knowledge base, but then two components that are unique to fuzzy logic are fuzzification and defuzzification phases. So at some point, you need to convert exact or precise values into fuzzy sets that are then used for reasoning. And the output of this reasoning should be again converted to exact values. So at the end, you need to have a number from this in this kind of inference. So let me skip this definition. So let's take this very simple example with how to use what to do with apples of different kind of level of readiness. So if they are overripe, so these are the rules that we have in our knowledge base. So, characteristics of apples and what to do with them. So we do cider, juice, or chutney, depending on how good they are. And that is what we do first with fuzzification. So we want to translate. So the input to the system is a concrete value. So again, later on we will talk about where this value appeared. So they can be appeared as part of the feedback loop in a technical system, or it's just another input if it's a kind of interactive expert system again. So I taste my apple. It's like, oh, okay, so it's like score 0.7. What I shall do? So you do fuzzification. So you describe, you have your fuzzy set. So with the three linguistic variables that are used in rules, and that's what you kind of get. So your input is exact value, and then you take you see what membership functions are activated, and what are the what is the value in the fuzzy range? Like for example here. So compare it to standard logics, I mean, or to propositional logic or to first order logic that we talked about. Here, it's not the single rule that applies for a given input, but rather you select all relevant rules that use these linguistic variables, and look at the combination of them. So, for example, so these are the rules of your database, and all of them. So we just made up example. All of them, they use this fuzzy set, so consisting of 3 linguistic variables to do something. And the input is the, well, de facto score or the value from the fuzzy range. And you apply these rules in to the extent of this indicated by the value of the fuzzy set. So, and as a result, you got another fuzzy variable. So basically, you can you're not sure what to do, but so you can do juice or you can do cider with this level of readiness, and this is why we need this last phase of defuzzification. So we need to to turn this kind of fuzzy concept into a single answer. So do this. So, and how to decide it? So it means that you need to have another membership function now for the defuzzification. Something like this. So this is a membership function, again, constructed having your target task in mind. So for example, so you build a system to assist you selecting what to do with specific type of product so that you can maximize profit, for example, when you sell it. And again, so that's another fuzzy variable. So or maybe not that fuzzy. So you can do some assumption on the model. So how much money you gain for this or that kind of sellings. But nevertheless, so you as an output of this preparation process, so you have this membership function. And that's what you do with the defuzzification. So you take again, so you consider all possible outcomes based on the result of your fuzzy reasoning. And there are different ways on how to deal with this. So for example, you can find a centroid of this area under the restricted curves or medium. So depending on that, so you will have a different outcome. So but nevertheless, so that will be your output. So what to do? And so now we come back to this question on where these values come from. So it really depends on the application. So there are control systems, very good examples. You can find on controlling underground trains in Japan and some other interesting examples. So you can build entire control systems based on fuzzy logic, and so I encourage you to look more details on the internet. So as part of this control process, so the process outputs the value, and then you have the it goes through the classification, so reasoning, so rules constructed again by experts, and so it outputs exact or precise control variable for the process. So what it can be there, for example, control so yeah, a current value of the current to your electrical motor, etc. I think people already leaving, so it's a good indication that we should stop. So let's continue next time. So we already start the next module on knowledge representation. All right.